Okay, with the quiz turned in, it's time to go on to new stuff. What we're going to look at today is we're going to continue with that finding missing pieces of a triangle. We want to look at something like, let's say we have a post that needs to be anchored. Let's say we have wires coming in that have tensile force on them, so to keep that post from tipping, we're going to anchor it with a guide wire. Looking at it, let's say the post to the point where we're going to anchor it is 35 feet tall. And the distance we have to work with on the bottom here is, let's say we can come out 18 feet. So I want to know two things. I want to know how long that wire is going to be and then what angle with the ground that's going to form. The length is actually pretty simple to find. How do I find that length? Pythagorean theorem. It would be the square root of 18 squared plus 35 squared. Gives us 39.36 feet. The angle, since that's the angle we're looking at, we're going to look at the rest of the triangle in terms of that angle. The 18 is what side of the triangle? Opposite, adjacent, or hypotenuse? Adjacent. The 35 is the opposite. Why didn't I use the 39.36? Yeah, that's one I just calculated, and so I rounded in that calculation. I don't want to use a rounded number if I don't have to. And also, there's a small chance that we made a mistake there. That if we miscalculated, that number could be incorrect. So we have opposite and adjacent, which is the tangent function. The tangent of an angle equals opposite over adjacent. So I'm going to fill in what I know. I do not know the angle. The opposite side is 35. The adjacent side is 18. If I were missing a side, I would put this over 1 and I'd cross multiply and divide. But when I'm missing an angle, I have to do what? I have to do an inverse trig function. What I'm solving for is inside the tangent, so I have to get rid of the tangent by doing an inverse tangent on both sides. So my angle is equal to the inverse tangent of 35 over 18. Which is 62.78 degrees. So that is that missing angle. Why is that angle important? Well, if we get that far before the end of the year, we're going to talk about vectors and vector forces. You know, if there is, let's say there is 400 pounds of tension on each of those wires. In order to keep this pole from bending, we need to have a total of 800 pounds pulling the other direction to keep that pole from, we want it to be horizontally neutral in the soil, if that makes sense. So the angle here determines what type of force we'll need. Well, let's just go through it. It's actually a really quick little demo. So here's our post. We need 800 pounds going this way. Here's our wire, and our wire is pulling in that direction, correct? All forces can be broken down into a horizontal and vertical component. This horizontal component has to be 800 pounds to counteract the 800 on the wires pulling the other way. This angle here is the same as this angle. So this angle is 62.78 degrees. So what we need to know is how much tension has to be put on that cable, that wire. That's this force right here. That's the hypotenuse. This is the adjacent side. We're dealing with a cosine. So we fill in what we know. We know the angle this time is 62.78 degrees. The adjacent side is 800 pounds. We are looking for the hypotenuse. Here is where we make this into a proportion by putting that over 1, and we just cross multiply. 1 times 800 is 800, and we divide by the cosine of 62.78. So 800 divided by cosine 62.78. So that cable is going to have about 1,750 pounds on it. It's just a tensioner. It's almost like they might have newer technology now, but it used to be almost like a wire stretcher with like a torque gauge on it, like a torque wrench does. So as you stretch it, there's a gauge that just goes as the force that's being pulled on it. Yeah, it's like a wire stretcher or a come along type deal is what it looks like. That has a gauge on it for pressure. Oh, sure. Okay. Other applications of this. Let's say you want to know how far it is across a river. There are two posts over here that you know are 20 feet apart. There's a post here. Well, let's just say there's 4 posts like this. These are also 20 feet apart. Let's say they used to form a bridge, so you know that they're square, that they form a rectangle. So that means you know that this here is a right angle. There's an instrument called a theodolite, or theodolite sometimes called, that you can set up at a location and you can aim it to another location and zero it out. They're electronic now. They used to actually have like a little protractor on the base that you read. And then you can turn it. It looks almost like a rifle scope, kind of like a transit. You can turn it to aim it at another location, and it tells you what the angle is between them. So let's say here you use that. You start at this post and you go to that one, and it gives you, if this post here is the vertex, this angle is 28 degrees. So we want to find what this distance is across the river. How are we going to find that? Well, we could find this angle is going to be 62. So now we have to pick an angle to focus on. Let's commit to the 28 degree angle. According to that 28 degree angle, we look at what we know. The side we know is the 20 feet. Which side of the triangle is that? That's the opposite, according to our 28 degree angle. Then we have to look at what we're trying to find. That's the x. What side is that? Adjacent. So those are the sides we're looking at, opposite and adjacent, which makes tangent. So now we write out the definition of tangent, and we fill in what we know. We know the angle is 28 degrees. The opposite side we know is 20 feet. The adjacent side is what we're trying to find. That's x. Since I know the angle, and I'm trying to find one of the sides, I make it into a proportion. So cross multiply 1 times 20 is 20, divided by tangent of 28. So 20 divided by tangent of 28, 37.61 feet. So that's the key. When we know the angle and we're looking for one of the missing sides, we make this a proportion by putting it over 1 and we cross multiply and divide. If we're missing the angle, that's when we have to use the inverse trig function. Well, since we've got that theodolite thing out, we're going to use it See if we can't destroy Mike's house. Hey, it's a 2-story cardboard box, though. No.
What?
Mike's got to cut down this tree. He's not sure, though, if he cuts the tree. He can't cut it the other way because, well, there's power lines there. Doesn't want to, drop it on the power line. Which, why not? You've lived a full life. That instrument called the theodolist not only can measure angles side to side, but it can measure what's called angles of elevation. So we can put this here and we can measure, sight it to the top of the tree, and it'll give us this angle here. Let's say that this is a 38-degree angle of elevation. Forgot how to spell elevation halfway through the word there. Yeah, that is, let's say that is 5 feet high. And let's say Mike measures from the center line of the tree, right below where that is. This distance here comes out to be, let's call it 89 feet. He wants to know how tall that tree is. Well, what we're going to have to do is we're going to have to cut this triangle off here. And we're looking at that triangle. So what we're finding is this dimension here, which I'm going to call x. It's not going to be our height. That only goes to here. So to find x, we know that this side is 89 feet. And we know the angle. So according to that angle, the 89 feet is which side? The adjacent. So we know the adjacent side. We're trying to find x, which is the opposite. So once again, we're dealing with a tangent. So I write up my definition. Tangent theta is opposite over adjacent. Then I fill in what I know. I know that the angle is 38 degrees. My opposite side is x. That's what I'm looking for. My adjacent side is 89. So I'm looking for a missing side, so I put that over 1 to make it a proportion. And I cross multiply. This time it's tangent of 38 times 89 divided by 1. So I do tangent of 38, make sure I close my parentheses, times 89, and I don't really need to divide by 1. 69.53 feet. Now we have to add 5 to that to get the height of the tree. So the tree has a height of 74.53 feet. What do you think? Would have been more fun to climb the tree? Sure.
And then measure it.
What you do is you play a gambling game. You have students bet to see how far they think the tree will reach, and you have them go stand where they think the tree will reach. And you cut it down and see.
There you go.
Yeah, but then Todd did the math, so he knows.
Somebody's got to work the chainsaw.
Yeah.
Well, since we're having fun with my artwork, we'll risk it. So since we're picking on Mike today, I'm sure he's so happy to hear that.
See him jump off a cliff.
Mike is anxiously awaiting a dear, dear person to him returning from a long journey. He is using his Theodolus. Yeah. He checked it out from the library. And he is sighted to the boat. Now, Theodolus has something called the Stadia Theory. Have you ever, anybody here avid golfers? You ever seen like a rangefinder for golf?
Oh, yeah.
It has like lines on it like this. And like they know the flag is 6 feet tall. So you look at it, if that flag fills up that space, that means it's 50 yards away. Or sorry, that means it's like 200 yards away. If it fills up this space, it's 50. Whatever size. Some scopes have those on them too. Yep. So it's called Stadia Theory. You actually use those and you can calculate how far it is to something. So Mike is sighting to this boat, and his dear, dear friend on the boat is almost exactly 5 feet tall.
Well, I realize pushing that.
280 pounds. And Mike sights it in the scope and in the Theodolus and comes up with a measurement of 1,380 feet to the boat. The Theodolus also reads a 13-degree angle of depression. Now, by depression, I mean, as in below the horizontal, not Mike's really sad that his friend's been away. So Mike is trying to decide if he can leap from the cliff to get to the water to swim out to his friend, or if it's too high up. So he wants to know how high it is from the cliff to the water. Now this time, since he's looking down, the Theodolus is set at only 4 feet off the ground. So he can see down through it. So we're going to look at this triangle here. This 13 degrees is also going to apply right here, because that being horizontal and the surface of the water hopefully being horizontal. Before he jumps, at least. Horizontal is parallel to itself. So since that's parallel, these two angles have to be the same. We're going to call this x for now, even though we're going to have to subtract 4 feet to get the height of the cliff. We have the hypotenuse now of 1380. X is which side according to our angle? Opposite. So opposite and hypotenuse are the sine. So I'm going to plug in what I know. I have my 13 degrees. The opposite side is x. That's what I'm looking for. My hypotenuse is 1,380 feet. We'll put this over 1, and we will cross multiply and divide. So sine of 13 times 1,380. Again, make sure you close that parenthesis after your sine of 13. Dividing by 1 isn't going to change anything, so it's 310.43 feet. But now, we got to subtract 4, you're right. Subtract the 4. So it's really only 306.4 feet. Terminal velocity for a human body falling, it depends on the position. In a cannonball type position, it's like 150 miles per hour. You can spread out and get slower than that.
So you hit the water, then you better curl up.
Yeah. The big question is, how deep is the water, right? It's at least 8 or 9 feet deep. You should be fine.
Water. Do a belly flop.
Okay, so yeah, Mike probably shouldn't jump from the cliff. That would not be good.
You got her.
There's friends for you. Oh, come on, you can do it.
Got it.
What are you worried about? It won't hurt me. Okay, now we're going to talk a little bit about job site layout. This is more on the construction side of things than on the telecom side of things. But let's say we have a feature that we want to line up with. Let's say there's a house right here. And actually, I'm going to do it over here to make it a little easier on us. We've got a house right here that we want to make sure we build a garage lined up to it. That's good. I'll go there. So we take our theodolus and we line it up with the edge of the house. Now what they actually have is they have like little things that like little stickies that you mount to the side of the house. They look almost like the sights on a rifle. They stick out like 3/4 of an inch or so from the side of the house. And you can actually sight right down that with the theodolus. Oops. So you get a perfect line down the side of the house with the theodolus. So you can get an exact zero line. So you know exactly how that side is oriented. And let's say you want to put, and I mean for you guys, it could be a pedestal or anything that you're putting out here, but you want to make sure that this is lined up exactly with that. Yeah, this is from overhead, yes. Yeah, I probably should draw this more like that so you see the stand down below it. We have to locate one of the corners of this building. So we're going to locate the one that's closest to our theodolus. And we're going to say from the center of the theodolus, that point is over 24 feet and up 20 feet. And what we're going to pour here, and let's say we are just going to pour concrete for a pad. Let's say that's going to be, I'll do a big one, 18 by 28. What's that? Is it that big? That's pretty huge. But
That's like the size of a CO.
yeah, it's 18 by 28 is pretty huge. Most of them are like 6 by 8 or 4 by 6. Oh yeah, that's pretty big. So anyway, to locate these corners, I'm going to use my theodolus. I'm going to go across here, making this triangle. I want to find the distance from the theodolus to the corner and the angle which it's at. So I'm going to call this corners A, B, C, and D. Corner A, the distance is just going to be A squared plus B squared equals C squared. So that's going to be the square root of 24 plus squared plus 20 squared. Does that make sense? So I'm going to cut some corners here. Square root of 24 squared plus 20 squared equals 31.24. So that's 31.24 feet. So A is at 31.24 feet at a direction of whatever this angle is. Well, this is the opposite side and this is the adjacent side, right? So that angle is just going to be the inverse tangent of opposite over adjacent, 20 over 24. Exactly. Yep, so 39.81 degrees. So we can locate that by turning this to 39.81 degrees and measuring out 31.24 feet. They'll locate that corner. Now, once we've located that corner, we can move to this corner. Actually, I'm going to change color. I'm going to use this one. This corner here. Corner B. What we know about corner B is this distance is still 24. This distance is going to be 38. How did I get 38 there? Yeah, 20 feet to here and then another 18 feet up to there, so 38 feet. So that distance is the square root of 24 squared plus 38 squared. So 44.49 feet. At that angle is going to be the opposite side is 38, adjacent is 24. So that'd be the inverse tangent of 38 over 24. 57.72 degrees. So I'd turn my Theodolus to 57.72 degrees, measure out 44.49 feet. Then get to my third corner over here. Do the same thing. It's not going to go through that corner. This is still 38. Now this is how much? $52, very good. 24 plus the 28. So that distance across there for point C will be the square root of 52 squared plus 38 squared. Would that be 62? No, it should be 52. So 52 squared plus 38 squared is 64.40 feet at, now our angle is going to be the inverse tangent of what? Opposite side would be what? 38 over 52. So 36.16 degrees. So again, you turn this to 36.16 degrees and you measure out that 64.40 feet to get to that corner. And then this corner is finally, corner D, do the same thing. This is still 52 feet. This, however, is now what? Back to 20 feet, right?
28. That's a 28.
This here is 28. You think it was 38?
Yeah.
Okay, yeah, that was 28.
I was,
No. Yeah, that's 28. So yeah, this here now, this is still 52 this way, but it's 20 this way now. We're back down to the original 20 because we're back to this corner. So that's going to be the square root of 52 squared plus 20 squared. 55.71 feet. At inverse tangent of what? From this angle, what's the opposite side? 20 over the 52, right? Yeah, a lot of stuff laid over the top of each other. 21.04 degrees. So again, you set the Theodolus at 21.04 and you measure out the 55.71 feet. And you've located those corners exactly. Does that make sense? If you're doing like multiple units,
So they all have to be next to each other, built square.
let's say you have a row of houses, and the houses don't necessarily have to be identical. Let's say here's your city lots, right? And you're going to put a PED in that northeast corner of every lot. You don't want to be able to stand down here and look down here and see them going down and up and down and up. You want to look down there, you want them at least pretty close to being perfectly straight down through there. And that's where they would line them up like that.
They need to do that with the rows of chairs at graduation.
They just look down them, but yeah, they're actually...
They still look horrible.
I know they do. For you guys, this isn't, like I said, this would be an application for you guys. For construction, it's way more important. You know, like for construction, if you have an existing house and they're going to build a detached garage over here, You might not think that if you're off by like 3 or 4 inches here and here that it would notice, but trust me, there are people that'll see it. Okay, so what I want to do, I believe this is in the packet I gave you. I gotta double check.
We did that test.
What's that?
We did that test.
You get tomorrow. You guys still have to see me tomorrow, right?
Oh, yeah. 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 Okay.
That's not the right packet.
We got this class and Martin. Might go into that satellite. Simplify the way it sounded.
I was looking at their calculations. I don't think that satellite's going to hack it. No, I mean, I really think they're better off getting a new satellite, to be honest.
Satellite or dish?
Sorry, dish.
Okay, I was gonna say, I don't know if they can afford new satellites.
Yeah, the dish isn't big enough. I really think that dish, I don't think that dish can be aimed precisely enough to make it work.
Yeah. Sounds like a shiny cut corner. I mean, I can't really blame them, but.
This is in the old packet, the old Smith packet. The old Smith. There's one that says New Smith. It's page 714 through 715. Exercise 35-1, 1 through 16 are applications of right triangles.
If I take off, I'm gonna go track down the hallway.
Go for it.
You're gonna what?
Track down the hallway.
Run track down the hallway.
Back down hallway.
You're
Holloway.
gonna track down the hallway.